Welcome to Video 7C, Week 7 Video C Supplement, which is how we would go about selecting a facility location using the weighted center of gravity method. So there's a lot of inputs that go into facility location, and they're very context specific. So it could be relate to the availability of skilled labor, unskilled labor, could be logistics issues with more detailed than what we're going to look at with the gravity method, could be the location of suppliers, the location of customers. There's so many different things that go into where should we locate a facility. But the center of gravity method can simplify one of the elements that typically go into that. And that is, if we're going to serve multiple markets or multiple customers from a distribution or retail facility, how do we decide where to locate it? So if it's a retail store and it's going to serve 8 neighborhoods, how do we know where to put it if we want it to be optimal for a distance traveled point of view? If it's a distribution hub and it's going to cover 7 states, how do we decide where to locate it to optimize the lowest transportation miles traveled or cost overall? So these are where the weighted center of gravity can be very useful. We're going to look at a couple of examples, and then hopefully you'll see it's not terribly difficult, but it is definitely something you're going to want to practice a time or two before an exam. So the weighted center of gravity method, our text defines a logistics decision modeling technique that attempts to identify the best location for a single warehouse, store, or plant given multiple demand points that differ in location and in importance. The weighting is going to give us a way to put some gravity into the importance factor. Okay, we use X and Y coordinates, and we basically compare the value of different coordinates and their weighting, add those up, and do some simple division to see where the center would be. This might give you a good feel for how it works. So Robbie Roberts, owner of Cup of Mo's Coffee, trying to determine where to locate his newest distribution warehouse. So he has currently he has the location and population of 3 towns that are going to be served by the warehouse. Those 3 towns are Capital City with a population of 400,000, Springfield with a population of 200,000, and Shelby with a population of 170,000. What these numbers next to each means is their X and Y coordinates. So we need X and Y numerical coordinates to basically help us drive where gravity is trying to center from, right? Where are these points? And what we're trying to do is use the population, in this example, as the gravitational pull towards each point. So you'll know automatically, thinking intuitively now then, that this 400,000 in Capital City is going to pull harder than the 200,000, half that, in Springfield, or the 170,000, even less than half that, down in Shelbyville. So it's going to have more gravitational tug because we're using population as the weighting. All right, so let's take a look at how the equation flows. So Robbie would like to locate the warehouse to minimize transportation cost, which he'll do by minimizing transportation distance in this simple model, and to get the best overall delivery speed on average to his 3 markets, right? On average to not equally to the 3 markets, but equally to his customers distributed across the 3 markets, represented by those population numbers. So we use X, we solve for X, and we solve for Y, using basically the X and Y coordinates for each of the 3 points and multiplying times the population, which is our gravitational number for this example. So we would take the 400,000 times the 1 here, right, because we're a 1 on the X, and we would take this 200,000 times the 4.5, right? right here. And we would take the 170,000 times this 4. So those are our 3 x coordinates and the 3 gravitational numbers, the 400, the 200, and the 170. Okay, so that will help us solve for x. And we basically would do that multiplication and then divide by the total of the 3 populations. So the 400 plus the 200 plus the 170 gives us this 770. Okay, how does that look mathematically? Well, the 3 multiplications added up, the 3 markets weighted added up are basically 101,980,000 divided by that 770, which is the raw 400, 200, and 170 added together, gives us an x weighted factor of 2.57. Okay, so if it's going too fast now, then just pause the video and look at the equations here. Look at the way it's built. Look at the 400 and the 1, the 200 and the 4.5, the 170 and the 4, and you'll see where those came from. It was the population and the x factor for that population. It was the second population, Springfield, 200,000, and its x factor of 4.5. Right, here's the 4.5. And it was Shelbyville's 170,000 population times its x coordinate of 4. Right, so multiplied those out, added them together, 1,980,000 divided by the raw total of the 3 populations, 770, 2.57. We would do the same thing for the y. We'll just be looking across at the y coordinates. So we have 400,000 for capital city times 5. The y factor is 5 for the capital city. The 200,000 times a 3. Right? Looks more like a 3.5. Looks like we got a mistake in the book here. That should be a 3.5. Okay, busted. And Shelbyville, their 170 times a 1. Right? Boom. Okay, and we would do the same method to solve for y. Do the multiplication and then divide by the raw, again 770, and what we would get is 2,770,000 by the multiplication and the weighting factors, and then we would take the raw and we would basically divide that out to 3.6. What is it telling us? Here it is. There's our star. 2.57 on the x. There it is. And 3.6 on the y. And it's telling us that if we locate here, if we take all of our customers in all 3 markets, that we will have found the average, the center of gravity between all of those customers. It's not the midpoint between the locations, it's the midpoint between all the customers. Given that we have many more customers in Capital City, it is moved closer to Capital City than it is favoring, these other 2. All right. If you wanted to think about, that weighting, what you could do is say, well, what if this were at a 0, 4 million? Well, this star would really slide up that way, right? These become background noise at that point. It couldn't go to the middle of town, right? It'd still be on the edge over here, but a large number here in Capital City would negate much of the effect of the gravitational pull of these 2. So these are similar, so it's just slightly biased towards Capital City. But if you skew one of these numbers, then maybe that's a good way to conceptualize it, meta learning, as we say, and kind of think what's really going on here. Well, turn one of these numbers into a big number, and this star is going to go bang. Gravitation is going to pull it right in. Okay, let's look at one more. And what I would urge you to do, if you do look at another, which I hope you will, because you need to be able to do this, you need to be able to learn this, is look at this example, and then after we just briefly talk through it, pause the video, do your calculations on the side, and then flip to the last slide where you can see the answers. So Whole Foods is trying to determine where to locate a new grocery store in the town of Chapel Hill. The grocery store is expected to serve 5 neighborhoods shown below. The XY map coordinates and the number of homes are shown below. So the gravitational number here, the weighting factor, is the number of homes in each of these 5 neighborhoods. So again, it's a customer count in this case. Doesn't always have to be, right? It's whatever we want to center on, whatever we want to have represented as the weighting factor. In this case, it's just a retail store, not a distributor, 5 neighborhoods. How many customers, generically speaking, right? Saying a customer is a customer in this simple model. Where should we locate? So we have the X and Y coordinates, and we've got the weighting factor. What you should do is pause the video, apply the same mathematics as we learned here, right, in this first example. Apply them to this second model, do your calculations, and then when you're done, click the video back on and go to the last screen and hopefully confirm that you got it correct. Okay, so here's a simple spreadsheet to show how you could do this in Excel. That's how I did it. Take your X coordinates, your cities, your neighborhoods rather, your Y coordinates, your number of homes, and multiply across. 6 times 90 is 540, right? 6.5 times 60 is 390. So take each one of these and map it out, multiply them across, and then take your Y coordinates. 2 times 90 is 180, 5 times 60 is 300, etc. And flow those across so that we've got the totals over here. Total them up. Get back here, you. I'm clicking ahead of myself. Total those up at the bottom because this is the number you need to do your division, if you recall. The 1505, the total of these X multiples, 1505 divided by the total of our number of homes in these neighborhoods, the 335, gives us a 4.49 for X. 4.49 on our coordinate map for X. And for Y, it gives us 1112.5 divided by the 335 is 3.32 for Y. And that's the solution to it, right? You could map it out. We did not map that one out, but you certainly could. Create a grid and drop it in like old Tommy Moe or whatever our buddy's name was that made the coffee there, Cup of Moe, and you could drop it in, right? And say, well, there's my different neighborhoods, drop those in, and then say, here's where gravity as a single factor, this is where gravity would put us. And you can take that information and make it as part of a decision process. Usually there's more to it than one factor, right? If we're going to set up a facility, we've got more going on here, more nuances than a single factor. But this is an important factor, maybe more important for some, a little less important for others, but a good solid method to help us make good decisions. That's it for weighted center of gravity as a location decision method.